Let's take a look at this logistic equation, which is a good replacement for growth and decay when we're talking about population. Because when we're talking about population, it kind of just makes sense to have a ceiling to our population, and this would allow us that ceiling. So this is our differential equation that we're looking at, and this is called the logistic equation. And then in our process here, we're going to solve for this logistic equation and come up with the logistic function. This is a separable differential equation, so we'll go ahead and separate that. And as we look at this integral, we see that this is actually going to involve some partial fraction work. So we take a look at our integrand. So that's p times a minus bp, and we want that to equal to fractions that are separated with the factors in the denominator. So we have unknown constants capital A and capital B, and we just want to remind ourselves that p is our variable. So if we find common denominators, we'll have common denominators. The numerators would look like 1 on the left hand side, and a times a minus bp plus capital B p. And if we sort this out, we get all the terms with a p in it, and this is being multiplied by a. So I will call this capital B minus little b times a, and this is multiplied times p. And then what we have left is the constant a times little a. And a times little a is going to end up equaling 1, and our variable p is being implicitly here multiplied by 0. So our b minus ba is going to equal to 0. So if our a times a is equal to 1, that means we have a value for our capital A, which is one of the numbers that we're looking for. That's 1 over a. And if we know that our b minus little b times a is equal to 0, then we know that b minus little b over a, that's capital A is 1 over little a, is equal to 0. So then b must equal to little b over a. So we got these two values. So we put that back into our differential equation. As we solve for the separable differential equation, we have 1 over a divided by p plus b over a divided by a minus b p. And so we're going to take the antiderivative of this, take the antiderivative of the other side. We're going to get 1 over a ln of p plus, this is going to be a b over a ln of a minus b times p. Now this actually involves a u substitution that would generate a negative 1 over b business. Because of the u substitution. Be careful with that. And that'll get rid of our b's here. On the other side, we will get t plus our constant. So after we take out that, and then we have a negative over here, we see that there's a factor of 1 over a all across the board, or at least on the left hand side. So let's multiply that out. Multiply this whole equation by a to get rid of that. And so we get ln of p. This plus becomes a minus. The 1 over a is gone. We have ln of a minus bp is equal to, now this a goes over to the other side, and this c gets multiplied by a. Constant times another constant is yet another constant, so let's call that c1. So now we can do some simplification work, simplifying. We have the ln of p divided by a minus bp is equal to at plus c1, and if we take the ln of both sides, we're going to get p divided by a minus bp is equal to e to the at, and then the plus c1 will generate another constant. Let's call that c2. So this looks like we're off to our differential equation here. The solution is coming up. If we can isolate p, that would be great. So let's attempt to do that. We'll get p divided by, let's multiply both sides by a minus bp. So you get p over here. You get c2 e to the at times a minus bp. And what we're going to do is we're going to gather all the p's to one side. So this is p, this becomes a plus bp c2 e to the at. And then what's left here is c2 e to the at times a. And so if we get p by itself, let's factor out a p, and then we'll just divide both sides. So this is c2 e to the at times a all over 1, that's the 1 taken out of here, plus b, and the p was taken out, c2 e to the at. Oops, this should be a b. So this is our solution to their differential equation. Right now it's a general solution. If we take advantage and use our information about our initial condition, we should be able to solve for C2. Let's see. I think it might be easier to find our initial condition here to get C2. So if t is equal to 0, p is equal to p naught. So we have p naught over a plus b p naught is equal to c2 e to the 0 power, which is just equal to c2. So c2 is going to equal to this whole thing. Let's attempt to put c2. Let's attempt to put this expression in for c2 and see what we're going to get. So we have p is equal to, this is a p naught over a minus b p naught times e to the at times a all over 1 plus b, and then here we have p naught over a minus b p naught, and then again e to the at. So the thing that makes most sense to me is to find our common denominators, so let's do that over here. Let's take this 1 and multiply it by a minus b p naught over a minus b p naught, so that we have the same denominator. So that's going to get us a big denominator in the bottom. Let's rewrite this as a p naught e to the at all over a minus b p naught. And this is looking hopeful because that's the same denominator in the denominator, which would be able to make us enable us to cancel. So we have a minus b p naught plus, Now this whole expression here has b p naught e to the at. So all that will be in all over one denominator, and this one denominator exists on top and in the bottom, so we can cancel that out, and then we're going to have simply our logistic equation. So we'll call this logistic function p of t is equal to a p naught e to the at all over a minus b p naught plus b p naught e to the at. Now the textbook does one more thing to this equation, and that is they bring this expression down to the denominator by multiplying the denominator by e to the negative at. So what's going to happen there when that gets multiplied by e to the negative at? Our final expression is just going to have a p naught on the numerator, and then now this gets multiplied by e to the negative at. This expression will disappear, will become 1. So we have b times p naught plus these two terms over here will get multiplied by e to the negative at. So we'll just group them together and then multiply that by e to the negative at. So this is our logistic function that comes from our differential equation. Okay, so this is a function that we'll be using for several applications.